Yeah. But sometimes, as long as he had fun, I guess that's what matters. As long as he did fun. That's fine, you're in.
So I didn't correct the homework yet. I didn't get kind of caught up. The other grade, actually grading the other class turned into like a long time, so whatever. Let's see. So I want to go through we've got like a week from today, Max Yan's gonna talk about like basically lithium ion batteries. I want to go through batteries, like just kind of battery stuff. And then the week, then we have Thursday. And the week after that, Sean Beam from Miami, Port Miami's coming to talk about the power plant there. And then 2 days from that, Mike Hoffman from our power plant is going to talk about like the grid or something, and maybe steam turbines, things like that. He used to be like the manager of Zimmer. So Zimmer was a coal plant. So it was originally designed as a nuclear plant. And they had, and it caused like a huge in the 70s. I think they had like riots about putting a nuke plant on the Ohio River. And then it was going to be a huge nuke plant, like one of the biggest one in the country. So they ignored all the protests and they went ahead and built it. But then GE built the containment vessel and there was a flaw in it. So they had to trash it. It cost $1 billion. They had to completely trash the nuke part of it. Then they decided to put like a coal plant. So because nukes are much more powerful than coal usually, like 3 or 4 times more powerful. So they had to build like the largest coal plant in the world, basically at Zimmer. It was gigantic. Anyway, the economics of coal tanked. Like coal is basically worthless now. Not from the environmental protests, but because natural gas, fracked natural gas is like 1/4 of the price. So all the coal is dead, completely dead. And all the coal companies are just trying to get out of it as fast as they can. So all the coal plants in Ohio are going to be shut. Anyway, all the coal, like that was the newest coal plant, in probably in the whole Midwest, and it was built in like 1970. So all the other coal plants were built in the 50s. And they have a lifetime of about 40 years. So basically, the coal plants that exist are running like 30 or 40 years beyond their planned extinction point. So they were dead anyway without rebuilding coal plants. They just are at the end of their lifetime. I think it's because basically, you can ask Sean, basically the pipes. So it's basically a huge room where they blow coal dust into, like basically barge levels of coal per day that they grind up into fine powder and they blow it into this huge room. And the walls of the room are like pipes, and they just circulate high pressure steam pipes through that, and they just torch the room. That's it. That's basically a coal plant. So it's a pretty amazing thing to see. So it's definitely worth going to Miami for it if you guys can do it. So the week, I think it's on like Thursday. Let's see. Of Thursday of the week after next, right? So we'll try to, hopefully we can get some carpools going or something. It's like Max Yan. Yeah, the week after next, which is like October. Sean Beam's coming here on Tuesday the 3rd. And the 5th is Mike Hoffman, and then this the tour of Miami is at like after class on that day. I think on Thursday, not on Tuesday. So we'll have to carpool out there. I mean, I can take like 3 in my car if anybody wants to go with me, but otherwise, we can figure it out hopefully. I mean, I'm expecting maybe like 10 maximum. But if you want to bring friends from anybody, just someone you met in the bar or whatever, anybody can go. It's definitely worth going. Like even if you know some environmental people or something, not if they're going to protest, don't do it. But just to see, because it's terrible actually. Like if you see it, you won't believe it. I mean, but if you like big kind of industry, if you like coal, it's great. Like it's heaven, But if you like burning things, this is a place to go. Like a steel mill and a coal plant. If you like burning stuff, that's where you should go. But anyway, it's good to experience it from whatever perspective you have. It's just see, because you run your life and you're just doing stuff and turn on the blender or whatever. You have no idea like what's going on down the river, It's been going on for a very long time. So it's pretty interesting. It's good to just know. I think everyone should go to a coal plant at least once, just to see. You can compare it too with the gas turbines and then compare it with the solar panels and wind turbines. Like people are talking about the birds in the blades and things. And like, if you go to a coal plant, you won't talk about birds hitting blades. That whole dialogue will end. Anyway, so I want to get the battery stuff though first here. Let me find it. Oh, the battery stuff is just in this thing. So I think I just took it. I would download it. Yes. I don't think I changed anything. Actually, it's probably just the same. Well, I can go through the homework next time, I guess, and I'll talk about what's the new homework. Let me just look for a second. Should I put up a new homework? Homework 5. Oh, we talked about EVs last time, like a little bit. There are only 2 people here. But anyway, this is in the Washington Post. I mean, it's kind of interesting. It's just like, when is it going to happen that everyone's going to buy EVs? Oh, all right. Yeah, see, I have a subscription to this. I'm gonna have to figure out a way to get this so you can get it. Yeah, I can try to do that. I think I'll just Google like how to steal a web page. Probably the easiest way. Anyway, that's not gonna work. But anyway, there's an article about.
If you copy and paste the title, sometimes another website will post the same exact article with the same title.
Oh, really?
It'll be.
All right, that's what I would find out. Maybe. Let's see, did I just close the whole Google? Yes, I did. Let me try that again. Let's see, homework 5, this thing. Okay, so you're saying steal this name. Just paste it in. That's the Washington Post. Yeah, you're right. ENH GM inside. Yeah, you're right. There's a bunch of them in Reddit. Is this going to actually work? No, I think no, it still wants money. All right, well, that seems like a pretty good idea. Oh yeah, this one would work though. Yeah, that one works. Well, no, it's only the first line of it or something. Oh, okay. Okay, maybe that's the whole article. I don't know. It's without the graphics, but so that one kind of works, I guess. Anyway, it's just saying like basically that it compares it with cell phones and talks about Norway. I think there's more to this article than that. I think there's some serious graphics in it, but there's plots at least. But anyway, I'll try to figure out how to do stuff like that to get those. Yeah, I think a lot of my things are Washington Post. Maybe a lot of them you can't get. New Republic's like isn't that an article? A newspaper? Oh, it's just like talking about it. Anyway, so it just says like, yeah, it's probably going to happen type thing. Yeah, it says like it already happened in Norway. Like Norway, 80% of the cars are electric. So that's the idea. Batteries are, I think, 175. There. Well, what is the homework? What is the homework? Did I just closed Google again? The homework has a question about that. I guess I didn't put the file up there yet. Anyway, I can talk about that next time too. That's pretty weird. All right, I'll have to get that. I think I'm behind the times here. Yeah. So anyway, just go through a little bit about batteries. So I guess it's a little weird because Tony was talking about lithium ion batteries, and mostly people, like when you're putting in a power, like a standalone solar, it's like deep cycle lead batteries are what people have used. But Tesla is selling this power wall thing, which is lithium ion. So, I mean, I think that I haven't price compared, but lead should be a lot cheaper than lithium ion, I think. But I haven't really price compared it, but they must be comparable. So, but there's other kinds of batteries too. There isn't just lead acid batteries and lithium ion. And there's some newer kinds of batteries like flow batteries, so these are a lot more like chemical engineering things. So flow batteries, you actually have two tanks, like a catholyte and an anolyte, and you have a membrane, so it's something like a fuel cell, except what's going on is a redox reaction at the membrane. Then you make electricity from it. And you can do that with iron, like iron chloride. So things that are really non-toxic materials. So lead is bad, lithium's bad. So there's a lot of like nasty things involved in batteries usually, but the flow batteries aren't. The other advantage of flow batteries is that if it runs out of power, you can just put a chemical in, like you can put the anolyte in, and then basically regenerate the battery without charging. So you can store as much of the catholyte or anolyte in separate tanks if you want. So you could store up energy for as long as you have tanks. Then just pour the liquid in and it just generates electricity. So it's kind of like almost like those are fuels, but they're regenerative fuels. You can regenerate that by charging the battery. So there's options. There's a lot of different options for batteries. That could be a situation, So for home use, I mean, it depends like how things are working out, but basically, I would think these flow batteries would be much better than either lead or lithium batteries, So anyway, so lead is like the most popular item. So that's kind of what I wanted to go through lead, and then a little bit of like the other batteries. And Matt's going to talk about lithium ion for one day probably, and then at some point we had talked about like, so when you did the thing, whatever the homework before the last homework, it was like figure out the cost for the system of the solar panels and the batteries and all the whatever. So charge controllers and things. It should have come out that the batteries were by far the highest cost component of the whole system. That was the point of it. But some people got cheap batteries somehow. Or they needed less batteries than it. Basically, the answer should have been like batteries are something like 3/4 of the price. So anyway, if that's true, then basically the other thing about batteries is if it's lead batteries, they're heavy, to transport. So if you have to ship them around the world from China to wherever in Africa or the US, then it's going to be easier to have like produce batteries wherever you are. The downside is that they involve a lot of toxic metals, right? So it's like, do you really want to get involved in the battery manufacturing process? So there is like a lead acid battery factory in Kenya that the British set up. So there is at least one battery factory in Africa. So and we were talking about trying to do this as a spin-off to the solar panel manufacturing thing. But basically, if you look at it, like with the kind of safety that you have in the developing world, and like it's not necessarily something that, and mostly it's going to be like a recycling operation. So existing batteries and remelt the lead, so you can reuse the electrodes, but you have to recast like connectors and things. So it's kind of messy. People have done that, like in Nepal. I have some pictures of the Nepal thing where they're making lead acid batteries. You can see like this videos and stuff, but there's also just pictures, and you can kind of see there's a lot of exposure to lead, and people aren't careful. So there's lead dust everywhere, and it's on their shoes, it's on their clothes. And these people have kids and they go home. So mostly it's like lead with kids, right? Kids get exposed to it in the developmental process. It impacts your like brain development. So anyway, so all the batteries are going to be kind of a redox things. You have reduction, oxidation. So reduction involves, like, usually you go to the ground state metal. Like if you take an oxide and you reduce it, you end up with a metal. So the reduction process is like taking your ore, then coming out with iron or whatever metal you want to get. Most ores are oxides, so they're kind of an ion, and you can reduce it. If you have another material that's got a lower electrochemical potential, so as if they can suck the electrons off. So every material has a certain affinity for electrons, right? So you can get a table of like kind of a potential to ionize things, like what kind of energy it would take to remove or add electrons to things. And it can be plus and minus relative to hydrogen. It's like everything's scaled to hydrogen, that's 0. And then you have these potentials to hold the electrons. Right, so you want something with mixed of a high and low potential to get the highest voltage possible. And then there'll be one cell. Right? So the battery means a collection. It's like a battery, like in the military, a battery is like a group of guns collected together, right? So this is like a group of these individual cells. Each cell in a battery is going to have like that voltage. The difference between the two reactions. Right? So you take the one of the electrodes will be like zinc oxidizes. So you take the ground state metal, you make it into an ion. If an oxygen combines with it, it'll be oxidation. So an ion plus oxygen would be oxide. So, or you can just, instead of involving oxygen, you just take the electrons away. Then you make an ion. So you start with ground state metal, you make them. These are transition metals. They can have different ionization states. Right, so you can go from ground state zinc metal to an ionization state where it's missing 2 electrons. That's oxidation. And then you can take an oxidized copper and then add 2 electrons to get ground state copper. So to remove the electrons, if you wanted to do this in a refinery to make copper metal from copper ore, you would use carbon, like you'd put coke in, and coke would draw off the coke has more affinity for electrons, so it would suck them off. Basically, you can do that reduction at high temperatures. Just pour the ore in with the thing with a higher affinity for the electrons, and you make the ground state. All right. So this kind of oxidation reduction reaction is used a lot. You'll see in the coal plant that they just blow ammonia into that big furnace. They blow ammonia in to pull the sulfur out. It's a reduction process. So reducing sulfur ions to sulfur ground state. And ammonia is the thing that's got the lower electric potential to pull the electrons out. So you just spray ammonia. Right? So this kind of oxidation reduction is used like all the time. Mostly it happens, this kind of thing, if you're doing it for refining, it's going to be done at a really high temperature. Like that, there's going to be a barrier to that process happening. You can put a catalyst in, like for water, splitting water, you put platinum in, right? Or you can split water at high temperature with 1.23 volts. So there's a 1.23 volt difference to make hydrogen oxygen from H2O, right? So basically that's also an oxidation reduction process. So all these things like fuel cell, electrolysis, batteries, cleaning up sulfur from flue gas in a coal plant, all those things are this kind of oxidation reduction reaction. They're all kind of the same thing, right? So anyway, so you can do this. You need a carrier, so you have it. Anion carriers like sulfate in this case, so sulfuric acid. It's like in a lead acid battery, it's also sulfuric acid. And then basically the anion can cross, the cations can't. And then the anions go across, and then because they're piling up charge over here, when the anion, the sulfates go across, then the electrons like flow through this circuit outside, and that generates electricity. If you turn the electricity off, then the anions stop flowing. So the current, the thing that you're driving here is driven by the affinity of basically of sulfate to go over and make zinc sulfate on this side by oxidizing the zinc, like pulling the electrons off the zinc metal ground state zinc to make a zinc ion. Right, so that's kind of like how batteries, all the batteries now work the same way, more or less. Except that in the lithium battery, so the lithium is lithium ions that are crossing across, and they form crystals kind of on both sides. So it isn't so much, it's not exactly like a reaction like this. Right, so there are nuances to this. It isn't always like exactly this kind of setup. Right? Like this is the reduction of, so you mine iron oxide and carbon, and this is an ion, so you're reducing the iron to ground state ion to make steel, right? And then you throw in a little bit more carbon, you make steel from the iron. Right? Like 0.2% carbon makes steel from iron with some chromium. But anyway, so that's also a reduction reaction, right? The minerals, like how you get silicon metal, initially you just also use coke to pull the oxygen off silicon, or you can use magnesium to pull the oxygen off. I think Max might talk about this magnesiothermal reduction of silica, SiO2. Anyway, so you pick and choose like what you want like to get for potentials in this kind of chart, and then you can mix two reactions. So lithium's a pretty good reaction, right? If you go into ground state lithium, it's like 3 volts. So that's the highest you can get. And also, lithium's the lightest material here. Right? So it's like silicon, lithium are light materials, aluminum, right? So basically, those are the things that you want to use in a car battery because you get a higher energy density, like kind of kilowatt hours per kilogram. Right? So other batteries, so like you don't need to worry about the weight. Then you think about like what's cheaper, like what's the cheaper material, what's the safer material, and what's kind of the lifetime of this operation of going through these like redox reactions, right? In other words, what happens in this process. So if you're producing well, in the charging process, you're going to be producing zinc metal, right, from the sulfate. So what form does that zinc metal take? Well, usually like it can form like dendrites. So and this isn't going to be like a package like in 2 jars. It's going to be in a cell, right, where it's all tight. So and the problem is if you get a short circuit across this membrane or this porous disc, then the whole cell just blows out because the current just goes nuts, right? It's a short circuited cell and it burns. It'll just catch on fire. I mean, it depends on how much power is stored in it. But basically, there'll be an ohmic heating of the thing and can just blow up. Right? So batteries can blow up if you get a short circuit across these things. So what happens when you charge it? So the zinc's going to go from zinc sulfate to zinc metal. And it's not necessarily going to be a nice rod, it's gonna be some kind of weird dendrites that form. And those are like spears that can pierce through this porous disc thing that they have here, or whatever separator membrane they have. Once that happens, then again, this is just packed tight, they're right next to each other. If any of that happens, then it just forms a short circuit path and then boom, lights up, So that's kind of the scenario of how, that's one of the problems. So there's a lot of problems with the different systems, depending on how this thing works. It's more than just the chemical reactions. It's like what physically happens to it when it goes through these processes. It can form, if you overcharge it, like in a lithium ion battery. So you have for the anode, you have graphite. Then this lithium ions like fit and intercalate, so go between the sheets of the graphite and fill in the holes. Well, if you overcharge it, then that lithium still reduces. So it's reducing to lithium metal inside the graphite. It's lithium +1 when it's outside in the solution. You're still reducing it, and it just makes a plate of like lithium metal on the surface of the graphite. So it just clogs it if you overcharge it. So there's a lot of problems like that. Like so it isn't just so simple. It can clog it. It can also form dendrites that pierce through the membrane and it blows up. Or if it clogs it, it just doesn't work anymore. Like you just have blocked the passageway, the physical pathway for the ions to get into the intercalated anode. And the same thing can happen at the cathode. It's also kind of an intercalated, meaning like layered structure where the lithium ions fit in the middle of them, right? So it's a little bit kind of more complicated than graphite. But so anyway, those are like a couple of the problems that can happen, right? So this terminal states of this metal ion ground state metal reaction that can make it not rechargeable anymore, right? So it'll be an end game for the thing. Anyway, so if you find the zinc sulfate, zinc oxidation and copper reduction reactions over here, so there's somewhere on this chart. Remember zinc and copper. Zinc is 0.76 and copper is 0.34. So those add together to like 1.1 volt or something. 1.1 volts. So you subtract those two, one's negative, one's positive, you end up with a voltage for one cell, right? So if you, like, that, and if you do that for lead, you get 2 volts for the lead reactions that happen with these reactions. That'll end up being 2 volts. So, but you have a 12-volt lead battery, right? So if you look in, I mean, there's 6 cells within that. So there's 6 of these reactions going on. It doesn't matter how large or small they are. So the 6 sum up, if they're in series, times 2 is 12. So you get a 12-volt battery. So any kind of lead acid battery is going to be multiples of 2 volts, depending on how you hook the things together. If you put more, so if you make them larger, it just means you can store more power in the thing. But it's always going to be 12 volts. It's not going to be putting more lead oxide and lead into it isn't going to make it any more higher voltage, right? You can get more amps out of it if you can get, so the amps, like how many electrons you get out is how fast this reaction happens, right? So the reaction is going to primarily be like the surface area of the electrodes. The higher the surface area, the faster the reaction. The higher the temperature, the faster the reaction. So you're going to get more current out of it with different geometries of the electrodes. So if you start your car, like if you have a lead acid battery, and you want to use it to start your car, so you're going to deplete it at about 5% to start your car. And it's going to recharge with the alternator, like when you drive down the road, almost instantly, right? Because you're only taking off like 2 to 5% to start the car. And then, so basically you're never going to drain it to 0. See, but basically you need to dump out that 5% like instantly. That's going to turn this big old motor. Like you have to turn around that big steel motor, like to flip it around. If you do that by hand, you'll know it takes a huge amount of power, right? So basically you're going to have a lot of amps coming out of that 12-volt battery. Because the amps times the volts gives you the watts, and that's the power, right? So you need this big amount of power to turn the engine. You don't need a deep voltage, but you're going to have to like dump it out fast. So you need to set this up with the electrodes are going to be like a grid kind of with a lot of surface area, as much surface area as you can possibly get for the electrodes, right? And then so then basically with that geometry, you can get a higher rate of reaction, and then you can get the power that you need to start the car. And then also will recharge fast too, because the reverse reaction will happen just as fast because you have a lot of surface area. Right? So anyway, that's kind of the basic idea. There's a couple other things like sulfuric acid evaporates. So this isn't pure sulfuric acid. It's like, I don't know, 1 or 2% in water. So basically the water can evaporate. So as the water evaporates, then the liquid level in the cell drops, and then your surface area drops because it's not coated in water, right? So in the really old batteries, you had to fill it with water. Like you check the water level in the battery to see if it needed water, and you'd go like, I don't know, every couple of years you'd have to put a little bit of deionized water into the battery. And then now this is just a gel, so it's a silica. So you can get organic silicon like TEOS, so tetraethyl orthosilicate, and you can react it. It hydrolyzes, so the ethoxy makes ethanol, comes off, and it'll make like a network in the alcohol. Like you can have an alcohol water mix, and you can make a gel. And it's a silica gel, so essentially like a nanoscale network of glass that just holds water. So that's useful for this because it can't evaporate if it's in, like Jello doesn't evaporate. Especially if Jello's in a plastic tub, it doesn't really evaporate. Whereas if you have water in a plastic tub that's kind of leaky, it evaporates eventually. But so it's basically they get rid of the aqueous and they make silica gel, which is non-reactive. Like glass is a good container for acids, nothing happens to it. Then you just fill it with H2SO4 water, and then that Jello doesn't evaporate, so you don't need to refill it with water. So that was 1970 or something. I think they came up with that idea. I mean, neither of those things, both of those things have been around since the 30s. So it just happened to be that. So there's a lot of room to make advancements in batteries, because if it took them 50 years to figure out that you could put Jello into it, that would make it so you wouldn't have to fill it with water. You can imagine there's a lot of things you could do to make this better, right? So it's not necessarily like the hardest scientific area to work in. And then to figure out, all right, so the good enough, it's the guy's name, he was at Oxford, I think, in England. And then he went to Austin, and then he went to New York, upstate New York, to Binghamton. And that's where like there's a big battery center there now. So he invented, he was the one that invented lithium ion batteries. But again, like how much did it really take to know, like, oh, you're going to use the lightest element with the highest potential to make a battery? Like, doesn't sound like that's obvious, right? So it's kind of like there's there's engineering nuances to it. But basically, the idea of a lithium ion battery, like you can just look at the table and look at the densities, and you'll figure out like, yeah, that's the way you should go, So anyway, I think he won the Nobel Prize with these two, a Japanese guy and some other guy, for that, because it's everywhere now, right? So everybody uses it for everything. So anyway, so apparently like lithium's one of the most common elements too. So it's kind of a good thing to use. This just showing like you add the two together to get the voltage for the cell. Then you're going to add cells together to boost the voltage to higher. Then the amps that you get out of it are going to be basically the geometry of it. And so lead acid is the thing that is popular, right? So lead's got the toxicology problems, and sulfuric acid isn't the greatest thing either. So it's kind of a combination of not great things in a sense, but basically it's cheap enough, I guess is what, and it's easy to mold it into pieces and things. So lead's given us 2 volts, like 1.7 and -3.1, right? So it's 2 volts. And then I mean, so it's higher voltage than like the zinc copper battery. And then so it's high voltage. It's kind of relatively cheap and fairly easy to work with materials, although they're toxic. You know, so it's got plus and minuses. You can also make a lead acid battery with a base instead of an acid in here. It's like sodium sulfate, I think you can use, which is like the stuff that they use for salt baths, whatever, Epsom salts. You can drain out. This is online. I have somewhere I have a Zoom of this or whatever. Right. You can drain out of your battery the sulfuric acid and put Epsom salts into it, and it works just as good. So you can do it. You can run the battery on a base instead of an acid. You know, and Epsom salts are a lot safer than sulfuric acid. So sulfuric acid is really cheap, though. That's the thing. Like it's super cheap. So it's kind of like the cheapest next to NaOH. It's like the cheapest thing. Right. So anyway, so it means you have lead, then you have to like make this lead oxide for the other reaction. Right. So it's basically going to be a process of just like lead plates and then lead plates coated with a slurry of lead oxide. And all this stuff is kind of like toxic. Right. So that's kind of the scheme of what's going on. It's a 2-volt battery, or 2-volt cell. This is just kind of a picture of what a lead acid battery is. So the question is like, if this is so easy, then why don't you just make it in Africa instead of importing batteries? And if batteries are the main stumbling block to alternative energy, so you already have like cheap photovoltaics, the other components aren't really that big of a problem. Need wiring. I mean, batteries is the main thing that's expensive, and it's difficult to ship it too, right? So basically, and you already have piles of used batteries sitting around in Africa and all over the world. Like, because people, once they wear out, what do you do with them? So you have like this toxic waste. So it's possible to kind of like recycle that stuff. These guys in this is from Nepal, right? There's some videos, but basically, this is what they do. They get the old batteries. They grind up these things. So basically, to get lead oxide, you grind up the lead in as fine a form as you can get it, which means you have this aerosol of lead powder. You can see they're working here. This guy has shoes on, but I think in the video, there's people, little kids walking around barefoot, and it's in Nepal, which isn't like there's different levels of poverty. You know, but Nepal is like kind of midland. I mean, I think it's like Central America poverty level. You know, so I mean, you can live there. It isn't so poor, you know, but, and also population density is pretty low in Nepal, right? It's cold, but it's kind of low. Anyway, so they're getting these old batteries. They just strip them out, and these electrodes are kind of all the same, you know. So they just take the old electrodes. They make their own little power, like battery cases. So each 2 of these plates is going to be a cell, and you add up like how many you want to get the voltage that you want, everything, right? And then they coat them with they paint them basically by hand with lead oxide paste, and then reconstruct the battery. And there's a separator, like a polypropylene sheet that goes between the 2. And that's about it. They take the old plates and they also make their own components using a propane torch and just melt the lead by hand. So it's like, well, you see there's nothing. He has nothing in his hands, no mask, like nothing. And he's just like melting lead and making whatever parts he needs from it. So it's pretty easy to do. It's just like, you know, would you want to be involved in an operation like that? You know, there's no PPE at all. It's just like totally kind of free for all. If you have a nice enough case, like nobody really knows what's inside of it, if it works, and it's not hard to make these work. So that's about it. You know, you can just sell that battery. They put a label on it. So anyway, so it's possible to do that. I think we kind of backed out of doing that. You know, that's like kind of insane. This is a real factory, so they have, you can see they're wearing like masks, goggles, gloves. They have aprons, no one's wearing shorts or anything. So they're semi-careful about what's going on with the operation. I think this is in China maybe, but and the company was comfortable enough that they made a video online to show you how batteries are made. So I guess they feel okay about this. I think the biggest safety thing is when they're working with the lead oxide powders, that there's some exposure going on. Anyway, so that's kind of, and a lot of the work now is done with robots. Like the plant in Kenya is all robotic. So basically a lot of the steps, this is a robot arm, like kind of assembling the plates. So there's less exposure. There's still some, but there's less exposure to lead. Anyway, so it's possible to do that. So lead acid batteries is still like pretty useful technology, for so let's see. Yeah, so basically the difference between a car battery and one of these is just the kind of the shape. This would be looking at a car battery with this high surface area electrodes. And the two electrodes are the same. One's just coated with copper, with lead oxide. The other one's pure lead. So that's that business. We looked at this. This is weird. The most interesting thing is the acronyms they use. So this is North America. This is Canada and Mexico and us. This is Europe, Middle East, and Africa. This is Asia Pacific. I don't know what C is. And this is rest of the world. So this is India, South America, I guess. APEC includes Indonesia, Philippines, and Australia. And row is rest of the world. It's pretty weird. Anyway, so I don't know. This is some kind of growth of, it's kind of a meaningless chart, but I thought it was kind of interesting, the symbols they use. Just the growth of battery use, renewable battery market type stuff. The steps in a battery plant. I'm not sure I'd do a tour of a battery plant. I think there's one in Chicago, but these are some of the machines for lead acid battery. So this is like how they make the plates that the Nepalese guys are using. They have like a lead printing machine that kind of prints the plates more or less. Then there's different, this is just going through like, there's two processes to make the lead oxide. So you can put it in a ball mill, or you can do some kind of chemical high temperature reaction. And depending on what you use, they make better or worse lead oxides for, then people have looked at the structure of these things, like the kind of like the chemical reaction happens on basically a nanoscale, and the oxide is some kind of structure like this if you blow it up. So like nanoscale, then kind of maybe submicron scale, then this is millimeter scale. So you kind of, this is going up in magnification and saying like, so the reactions that happen in down here in these processes, like the ball milling and this kind of chemical process, can lead to different microstructures that can affect the kind of the rate, I guess, of the reactions that are going on at the oxide electrode. The lead electrode is just solid lead, so it's not, doesn't have the structure to it. But this is a picture of the alkaline cells, like the zinc manganese cells from here. So it's kind of how it's put together. It's the same idea, like oxidation reduction reaction. Two metal oxides, and there's an electrolyte in the middle. So this is what this flow, kind of a schematic of the flow batteries. I think to me, this looks like the future of solar stuff. Right, so first off, like why Tony didn't talk, why he's talking about lithium ion batteries when lead acid would be cheaper. That's kind of like one thing that's kind of weird. And then the other thing is if you're going to go to like a higher tech, like this is going to be a better bet. Because this thing, for one thing, these things never, in other words, these are forever. There's a battery that doesn't die. The flow battery never dies. So you can completely replace the active ingredients of it. So the actual system is like a couple pumps. Right. So you need to have some power, like if the power goes out, you need to have like some kind of residual power to drive these little pumps, but they don't take much power. So you could have some like lead acid battery. Initially, you need to start it up with some power. But once the thing starts running, then it generates electricity and it can power its own pump. So you might need a little car battery or something to keep it for startup if there's a complete shutdown. But otherwise, you're just flowing these liquids through it, right? So there's a variety, like people have looked at a lot of different analytes and catholites in this thing. There's like zinc, a zinc bromide batteries, one of them. And there's these companies, these are like companies that make flow batteries. You can buy this whole system. I mean, they make them in a semi. So you can put the whole battery into a semi. Inside the semi, it's like this. It's all PVC pipes. There's 2 tanks, and then there's a bank of these membranes, right? And then you just have electrodes that come off, and that's it. It's a gigantic 50 kilowatt, 400 kilowatt hour, I guess, battery in that semi, you know. So this is one of those batteries in place, like where it's being used at like a vineyard or something. So like they have solar cells and they have this flow battery and they run off each other. Anyway, this company, let's see, this might work. They're using this iron chloride system. That's the same problem. Open this. Copy link. Over here. That didn't work. In here. Open link doesn't work. Copy link. Did that. Get the link. One more try. Different approach. Doesn't have like edit link. I enable editing. That's why. Well, now if I go copy link, it probably works. I've already gone through this once, the same exact thing. So it's like, you can't teach the monkey how to do anything.
How to get the most of Grandma.
This is just a company. The guy's talking.
You by ESS Inc.
This is a few years old, like too, but
This is a vineyard in Sonoma, California. The solar panels you see there power the irrigation. Next to it, underneath that tree, is a battery. But it's unlike most batteries you've ever encountered, because it could power your house just as easily.
wow, this guy's like a joker. He goes on and on.
Called an iron flow battery, ESS's design promises long-duration, large-scale energy storage with little to no environmental impact. And it's all possible because of the unique chemistry of the battery. It's mostly water. But first, let's talk about why we even need a new kind of battery.
So what we do here is, essentially we're trying to change battery technology.
The batteries you're most familiar with are small. They're in your phone. They fit in the palm of your hand. But we need
Blah, 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 blah.
chemical cell where two chemical solutions are separated by a membrane. Ions are exchanged across this membrane, producing chemical energy and electricity. See that shipping container? That's not only used to transport the battery. It is the battery. That's right. You can go inside it. And that's exactly what I'm going to do.
Yeah, so now you're coming into our containers. So if you turn around, look over there, that's where we store the energy. So you think about this 40-foot shipping containers are really,
So a Chevy Bolt is 50 kilowatt hours, and this is 400. So this is the battery equivalent of 8 cars? Give you a rough idea, you know. It's kind of like 8 car batteries in a trailer. So it's large, like it's bigger than the cars. If you just took the battery part of the cars, they would stack and it wouldn't be that big. But this is like so cheap. There was just nothing to this. It's just like iron chloride solution. You can buy it, you know, off Aldrich. It's like nothing, right? So this is really cheap, and also it's like totally safe. Like this will never blow up. And you can take the liquid that's in it, you can spray on your lawn and it'll make the grass greener. Literally, you know, so there's a lot of advantages to this.
separate a half and half. One half is basically all the chemicals I use to store energy is in there. And then the other half is what we call the power module half. So the battery module is there to make the electricity happen.
Called an energy warehouse, ESS's design is particularly well suited for long duration storage up to 4 hours or more.
And so there hasn't been really a need for long duration storage up until this point because there hasn't been a large prevalence of renewable.
They're selling it to the military. That's what he ends up saying. Like basically, this is vineyard, and then they're selling it to the military because you can truck these things out. So it'll hold it. Also, it stores a charge forever. If you turn it off, you have 2 vats. They're 2 chemicals in polyethylene drums. So it will store that power forever. You can bury it in the desert, and when there's Armageddon happens, you can go there and you can get 400 kilowatts in 2080 or whenever Armageddon is going to happen. Right. So basically, if you're looking at end of the earth or some kind of nuclear war, this is your option, you know, because the lithium ion after 100 years is not going to be anything left, right? So basically, this stuff will still be there.
Renewables being put on the grid.
there's a lot
But
of-
now with the large
also,
duration of
it's like-
renewables, you now need some way to shift bulk amounts of electricity.
Blah 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 blah.
Problem. We do not, right? There's no fire risk.
He shows the military thing at the end somewhere. Other than that, like that's
The way we look at it is when you're utilizing,
like showing like how you make a lithium ion battery. Like you need all this mining and all this stuff. Whereas iron,
PVC
I mean,
plumbing.
iron chloride is like the first step after dissolving a rock. Like you put rock into HCl and you get iron chloride. It's like there's no. He's right. Like there's no processing it.
Sometimes when we're missing a part, so a certain part didn't come in, our engineer would just go to Home Depot, pick up the different parts and make it happen.
Not a sponsor, Home Depot. Okay, so now
Anyways, it's kind of. I think it's kind of interesting. So this is just one example.
the Corps of Engineers is currently testing ESS's design to see if it can effectively reduce the military's dependence on fossil fuel. And a few iron flow batteries have even made their way to Europe and South America. What do you need to do to take over? What needs to happen? Get the word out?
Getting the word out is one. I think,
Man,
you know,
it's like
we've
a niche. Anyway, it's a niche battery, but definitely like if you have solar on your house, I mean, should be an option that you look at, like, because, well, he's talking about, that's 400 and he's talking about a 14 kilowatt hour. So it's like much, and this scales too, like you can make small or large scale of this, doesn't matter. I don't think it matters what size scale you make this thing. I mean, you wouldn't use it for your computer unless you were camping or something. I don't know. All right, you could take the iron chloride and just add water. You need deionized water. So you need to have like a thing to filter the clean water or something. So you could think about camping, haul the powder with you, have a thing, you can make deionized water with a filter. So just take the stream water, pour it in, then you'd have like your 10 kilowatts, whatever to run, whatever you want to run. You know. It's possible to think of this in different scenarios where you could use it, but for your house, I mean, it's the safety factor. It's not going to blow up like lithium ion. If you get these dendrites going across it, it's possible it could torch your house. I mean, it could happen. this thing, there's no way, like it would just fertilize your lawn, that's it. So I mean, there's a lot of promise to the, wait, why don't we quit there? Then I might have a couple other things to say about batteries, but I'm gonna try to just talk about coal plants next time, some kind of coal plant thing, so.